So I want to thank Axel also for contacting me about this seminar. And this is very... This way? No. Oh yeah, a bit more force. So I'm just showing this slide to see that what I normally work with is asymmetric catalysis. So it's not so much into origins of common chirality or this stuff. Usually what we do in my group is to try to make reactions, static reactions that are following these criteria. Try to prevent waste and to be non-toxic, atom economic, minimize energy, start from renewable starting materials if possible, and use catalysis, and also to achieve high stereo control. So you all know here that as from the Vidma talk, it was a nice introduction about chirality, the importance of making asymmetric catalysis to get, for example, pharmaceuticals. And in this case, it's one enantiomer of this drug to be active while the R enantiomer is inactive. So in this case, by chemical synthesis, we can create one of these drugs. So what do you look for? Inspiration, and who is following all these criteria that I showed from the beginning? That's actually nature in our cells, which are catalyzing conversion from carbon dioxide, ammonia, water, and use energy and light. And it creates here a lot of reactions going on, and it creates different types of molecules. For example, amino acids, this hexose sugar, or this nucleoside. And all of them are, as we heard from this talk, are one single atomless. And in this case, it's only one asymmetric center, but in this case you have 5, and here you have 4. So this is just pretty amazing how nature can assemble. And to understand this, I've learned a lot here on this talk. There are different ways, and it can also be applied actually in catalysis, the things we have been listening to on this seminar. So I'm showing you this slide. This is actually what's going on in that vessel, that simple reaction vessel. And actually what we are doing as humans every day in our body, every second. So this is, we had it at home in my family. We have some medic persons that are involved in medicine. So when I grew up, we were looking at this map, and you can see it's amazing. There's a lot of reactions everywhere. Mm-hmm. And the body is controlling this. So I have this. So it's more simplified what's going on in our cells. So everybody is a chemist without even knowing it. So we do this reaction. For example, here we build up sugars by using gluconeogenesis. We break them down by glucolysis. And there's a lot of steps here which are we use in chemistry as well. And here we have the energy and the citric acid cycle. And all these are catalyzed by enzymes, which are of course chiral because they're made of L-amino acids. And they're making sugars here, which in the first step, in the first aldol reaction, makes it D sugar. And then it could be different diastereomers, as you know. So we have different sugars, but they're all D because of the first aldol reaction. So I'm drawing this more simpler scheme then, because this is what we chemists and nature will do to activate carbonyl compounds. And carbonyl compounds are one of the backbones in synthesis. So for example here we can have an amine to react with this carbonyl compound to form iminium ion, and then this becomes electrophilic. But you can also dose this proton here and you make it an enamine, and then you make this center nucleophilic and you can attack an electrophile. Or you can have a metal ion, you get the Lewis acid activation, it becomes electrophilic, or you can make this enolate for nucleophilic attacks and electrophiles. And also you can have simple Brensted acid, which protonates this, or makes this enolate, or even simply just hydrogen bond activation to activate carbonyl compounds. And all of these type of strategies are used by chemists and also by nature. So if you look at the aldol reaction I talk, which is the direct incorporation from amino acid with carbonyl to make sugars that we talked about. So here we have, for example, type 1 aldolase enzyme. And type 1 aldolase enzyme produces an lysine as the active residue. But in the first step it forms this iminoion with dihydroxyacetone phosphate, as you see here. And then it will read you selectively, only deprotonate this here. So you get this chiral enamine. And then you make a carbon-carbon bond forming reaction. You regenerate this iminoion. And upon hydrolysis, you generate a sugar with 2 new chiral centers here. And out of 4 possible enantiomers, the enzyme is doing only 1. And here is the active site, actually, you can see. So you have the chiral environment by the amino acids, which will generate what you get here. Then there's the second strategy that nature uses, and that's using zinc inolates. For example, using the zinc as a Lewis acid. In that case, you have only a chiral environment from the amino acid, and this purple compound here is the zinc ion. And then, after you make the inolate, once again, read you selectively only on this side. And then you make carbon-carbon bond forming reaction, and you get your sugar here. In this case, they are keto sugars. Okay. So here I'm going to some pioneers in carbon asymmetric catalysis using carbon-carbon bond forming reactions. And here you have Evans or Jevison using these type of copper pi-box complexes. And by activating the carbonyl compound, Lewis acid activation, and using this preformed TMS inolate, you can make aldol reactions. And they are called indirect aldol reaction, since you have to preform this inolate. And then we have in Japan Shibasaki, who makes the first direct asymmetric catalytic aldol reaction. Oh, well, not with Lewis acid, using zinc, for example. And in this case, I've shown a manic reaction. And in that case, you're mimicking the type 2 aldolase because they have zinc ions for activation. And then also you have Barry Trost, who has made this type of ligand, using 2 zinc ions as well, and using proline derivatives on both sides here. And what you can see here is, in this one you get anti-selectivity, and in this case you get syn-selectivity. And so this is different ways of direct, but this has been known for a long time, the direct aldol reaction. And here I'm showing you one of the first ones, presented independently by Hires Parrish and Ederwich and Sauer in Germany. And this reaction was developed, that I show here, by Hires and Parrish. And this is an intermolecular aldol reaction catalyzed by a small amino acid like L-proline. You see it's used catalytic amount. And it gets this aldol product with 93% EE. And upon dehydration you get V1 ketone, which you can use for protein synthesis, but also high enantoselectivity, this center, because they have high DER. Okay, so what they proposed were 2 different types of transition states for this reaction. So directly asymmetric. And here you see one, they have an amino catalyzed mechanism, so you have a protonated amine which will attack this carbonyl compound here. Or, as Agamile proposed, you can have 2 protons, or 2 proline molecules involved in this transition state. And that's where also Professor Kagan got involved in this, because according to his theory you can show that there are more than 1 molecules in this type of transformation. But now, later it has been confirmed and also established, I believe, that there's only 1 molecule in the transition state. It's a carboxylic acid catalyzed enamine mechanism by Hauk and List. This is what they propose now, is the transition state. So also List, in 2000, there was nothing happened in this field more than the intermolecular aldol reactions until year 2000, when Ben List and co-workers published a paper on using L-proline at much larger excess here, but nevertheless you get this aldol reaction to go, and isolate this by beta hydroxyketone with 76% EE. But that you can change ketones and then the EE can dramatically increase, as I will show you later. And he also developed the first 1.3 component asymmetric manic reaction that you see here, which also has been presented in this conference actually, similar type of reaction. So when I got involved in this research field, it was trying to mimicking the aldolase enzyme DERA, which is quite interesting enzyme because that's the only one who is catalyzing carbon-carbon forming reaction using aldehydes as nucleophiles. As you expect, that's a pretty tricky reaction because aldehyde can both be an acceptor or a donor. So, but the enzyme is only using acetaldehyde as a donor and nothing else. In that case here, what I show you is a sequential aldol reaction, and in that case it forms this sugar with high selectivity. So when we try this reaction using acetaldehyde, try to form this compound, we're not so lucky. It's hard to control after the first aldol. So we got 5-hydroxy-2-hexanol, that's kind of low yield, but nevertheless an 82% E, and mostly this diol. So we got the products. But it showed that you could start to work this. And now, 2 months ago, Hayashi in Japan showed that you can control this type of cross-aldol reaction with acetaldehyde, but then they use a proline derivative. So the field is developing. The next step what we were doing is to work in this, to try maybe we could work with other electrophiles, which is, for example, this PMP PMP protected alpha aminoglycolate, as you see here, in order to make amino acids. So we try this reaction, and you see once again aldehyde using proline, and we make the manic, and we get high syn selectivity and high selectivity for this reaction. And it also works for using ketones, which we publish in a separate paper. And as we heard, it's not here, Gunther, I think, today, but it has some interesting abilities, this type of transformations. Okay, in parallel, Macmillan, then at Caltech, is now at Princeton, published this paper, which is very good, where he used self-aldol reaction. In this case, when you use propanaldehyde, proline can direct this reaction much better, as you can see here. And here you got this beta-hydroxyaldehyde with high DR, or good DR in this case, and high enantioselectivity. And in this case, you get excellent diester selectivity and excellent enantioselectivity. And these compounds are very useful for synthetic purposes, in total synthesis, for example, of natural products. So kept on going this research, and we tried to maybe we can do this similar type of transformation using a 1.3 component manic reaction. So we tried this reaction, and what you can see here, you have excellent diester selectivity of the product, and also excellent enantioselectivity of this transformation. So there's a lot of competing reactions, but nevertheless, at minus 20 degrees. Proline can direct this transformation. So, the scope of this reaction is that you can see here you can have aliphatic donor aldehydes, and usually you have aromatic acceptor aldehydes, but you can also have alpha glycolate, and you have aromatic anilines usually as the amine component, and then you get this reaction with high yields and high selectivities. So what is the mechanism of this reaction? So I'm going to show you the mechanism of the manic reaction with a 1.3 component reaction. And this is actually much more complicated as we know today, but this is the simplified version. So what's happening is that proline comes in here, first forms an iminium ion, which I have not shown here, followed by deprotonations to get this enamine, chiral enamine intermediate, and then on the other side in the reaction, anisine is chemoselectively reacting with this carbonyl acceptor to form this imine in the 1 point. And that's much faster than what a proline will do, because otherwise we wouldn't have a reaction. Next, this chiral enamine is reacting with this imine, and it will form a selective carbon-carbon forming reaction here. And this is this small proton here, this handle, which directs the stereoselectivity. Next, water comes in, and upon hydrolysis, it will regenerate your catalyst, and also release the product. And as you see, it works like a same mechanism as for the aldolase that I presented type 1 in nature. So if you look at the transition state of the aldol and the manic, this is the aldol transition state here. You have the chiral enamine, which have a trans configuration here, like this. And then so it's C phase on the proline here. And then the aldehyde is coming in at the re phase, which means it comes from this side, with the R group pointing away to my direction. And then you get an anti-selectivity of this reaction. This is this carboxyl group which directs the stereochemistry. In the manic type reaction, instead of this re phase of the imine, you get the C phase attacking. It means that the R2 group is pointing away from me. And that is because if you switch that to re phase, you see this big aromatic group, parametoxyphenyl group here, will interact with the carboxyl group here. That will create repulsion, and that's why you have high syn stereoselectivity. Okay, so what we developed also is this more, even the first classical manic type reaction using formaldehyde as an acceptor. And in that case, you only generate one stereocenter with excellent stereoselectivity, as you see here. And what we thought then, maybe we can take this further. If you take this reaction and we react with an alpha-beta unsaturated ketone, maybe we could get sort of like a acyl-aldehyde type reaction, as you see here. And what's interesting with this reaction is that it brings in, it's like a domino process, so it brings in two type of activation mechanisms. And this has been done by, also before us, by Yamamoto, using nitrosobenzene. So that's how we got the trick. So you see this, you use the proline, it will form a chiral enamine this time. And meanwhile, as in the manic reaction, this will form the imine. And then you make the manic reaction first step here, exactly as I showed you before. But then, since you have alpha-beta unsaturated ketone here, you have this iminium activation, as you can see there. So this will do an intramolecular Michael reaction, and you generate your bicycle here. And upon hydrolysis, you get your product, bicyclic product here. And it's the same transition step in the first step, which directs the stereoselectivity. So it's a domino manic Michael process. So inspired by this type of chemistry, which is kind of natural-like, we work with a lot of different compounds. I will show you a few reactions, and this is what we usually are involved in. So heterocycles, carbocycles, cyclopropanes, acyridines, oxysilidines, and phosphoradditions, for example, is what we have done. And you see, all commonalies are high selectivity in that we have used different amino acid and proline derivatives here. So now, let's go for the origins of chirality as the lecture is. And sort of they are connected because amino acids and sugars are in that's what we need for life. And what you can see here, here's one of the first transformations using nitrosobenzene. What the goal of this reaction was is to do alpha aminoxylase here, to introduce an oxygen here. What you get then is alpha hydroxyketones or dihydroxyketones here. And as you know, they are very important for making sugar synthos in our body, or to make glycoaldehyde, for example, if you don't have the R group here. But then you have this NH. But nevertheless, this reaction was developed independently by these groups, or ours too. And what you see here is that you can get it with excellent stereoselectivity. So we're thinking more after you have developed this reaction, which is that before I can show you, we do also some transition states here, also calculations. And as you can see, why we get this high stereoselectivity in this, the same as you have the only discrimination factor here is that you can have either E enamine here or C enamine when they are on the same side. And as you see, only this direction here, this angle here, and the hydrogen, this angle for the hydrogen to the nitrogen, we generate 6.6 kcal in the aldehydes. So that's why you have so high selectivity. But in the ketones, even the higher, 7.2 kcal difference in transition states. Just of this dihedral angle, that you have difference and also the distance between the nitrogen and the oxygen. That's the origin of the stereoselectivity of this reaction. So what we thought next then was, this is not so good with nitrosobenzene. It's kind of dangerous, not so good chemical to work with. So maybe we can do something with oxygen. So I read some papers, and then they did some singlet oxygen reactions, but they were ene reactions, but you can also use nitrosobenzene. And then I said, maybe we should try this. Maybe a chiral enamine could react with singlet oxygen, which is electrophilic. It's not longer in its triplet state. And then it maybe could incorporate it at the alpha position. And if you can do that, you obviously see you get, for example, if R group is gone, you get glycoaldehyde, and then it's not chiral. Or if you have R group here, you can get chirality at the center. And these products usually oligomerize, because this is unprotected, and you can oligomerize with aldehyde here. So we reduced it, and then we get diols, as you can see here. And then at that point we also start to use primary amino acids, and we saw that they can catalyze this reaction. And recently we found using this type of catalyst, which was developed by Hayashi in Tokyo University and also by Karl-Anke Jørgensen in Aarhus University, we can actually control this reaction pretty well. Up to 98% DE using such a small acceptor electrophile. So based on this, we got into also origins of life, of course, because we were thinking in terms of, could you use this starting materials to make sugars with high selectivity? And then Sandra Pisarello published a paper in Science where she used glycoaldehyde and linear amino acids, and she got sugars. But you see, the E is very bad for this reaction. But if you protect this sugar, you can get hexoses or tetroses with high enough selectivity just by using amino acids in organic solvent. That works though. But in water, as you can see, the simple amino acid gives poor E.
Which amino acid?
Every works. They just erase. All natural. Unnatural. So but I can tell you that all amino acids works. But the rates are very slow. But they will work. And they will also give E. But they're 14 to 0. So the E is not good. But the next step was, you see here is the Macmillan reaction, the first step here. Using aldehyde this. So you get the tetrose. And then we thought maybe we can make a sugar, because it should be able to react once more. And actually if you heat this, and this is aliphatic, it can go all the way, but then you get the hexose with poor selectivity. So we were thinking, what can we do? And then we did it stepwise. So we changed the selectivity of this one, and we get this not so good yield, but nevertheless it can do one additional, and then you can isolate the hexose sugar with high DR and high enough selectivity. And that's because of diastereoselective interactions favors no further reaction for this. I'll show you later why. So that was the next. Then we also started to read literature, and as we tried to do nonlinear effects then. We read the famous paper by Kagan about nonlinear effects. We want to look into our reaction we see in sugars and tetrose. And it's very interesting, that reaction, because in the first step, as you see, if you look at this one first, you see it's like sort of like a S shape on this one. But then if you apply free, it goes up with huge asymmetric amplification, as you can see here. So then we became intrigued. What is going on? We need to understand this, because it's a pretty interesting phenomenon, and it could be related to what for this lecture, topic 2. So we take a much simpler system that I showed you already, just dimerization of propionaldehyde, and check the same thing, E with dependence of the product E. And you see here also asymmetric amplification. I have to tell you that all these systems are homogeneous. Also asymmetric amplification. So what is it? We start to believe that there's something involved with the product, of course. But it can't be just autocatalysis, because this product does not catalyze this reaction. We have tried that. So what is going on? There's no amine here in this product. So we start to think, what can we do? So we made up a scheme like this, and according to this scheme, you can have, it could work for a parallel reaction or the sequential reaction, and also for an autocatalytic, of course. So it's simply that if you have the first cycle here, you have the amino acid with certain E, first catalytic cycle, and then you get the product here, and this product will react with your catalyst and resolve it in the solution. So you have in the next catalytic cycle, you have a higher E of the amino acid, and then you get amplification of the enantiomeric excess. Or if it's a completely parallel reaction, that this reaction is going on and makes a product which also resolves the catalyst, you will have an enantiomeric excess in this catalytic cycle. So it can be two completely different reactions, but you will see the effect based on this product for the other reaction. So then we thought, okay, if this is true, maybe we can do it with racemic amino acid by throwing in a chiral product, for example the tetros that I showed you. Then we should get out a product from a completely different reaction. We will get it with the enantiomeric excess, of course. So let's do the test. So we did this reaction, and this one, without this one, we give 0% V of this product. And we have also checked the linearity of the system, and it's linear. So we throw in the sugar product, so we use natural sugars here, and also sugars that are made from S. proline. And what we found is that they can resolve the catalyst, and you get E on this product here that I show you on this slide. And depending on the time, because this is kinetic effect, we can increase it if we optimize it to 66% E on this product. So we can get pretty high E by using this one. So what we think, and also we are established by mass spec, is that this is also should be an equilibrium arrow back and forth here between these two, is that you first form the aminium with the product that you're creating, and this product could undergo oxidinone formation here, and these rates are different depending on if it's S. proline or R. proline. And here I've written the stereochemistry of the S. proline derived product, and as you can see then that we see this amplification, then the S. proline reacts slowly with this product, while the R. proline reacts fast. And that's why we get in solution, get the high EE of the free S. proline. And then, of course, in the next catalytic cycle, we have the amplification. So we also did kinetic effect studies on this, and this is based on NMR studies. So if the black one here, this curve, is just without this 2B, we didn't add 2B here. And then you see it's fast. And then we added, we did the reaction with the S. proline, and we add 2B. And then you see here, it's slowed a little bit, so it interacts with the dimer, but you still have not so bad rate. And you see also the difference gets bigger with the rate, with time. So we throw in this product again, and we did the reaction just with R. proline. And then you see that you dropped much more here. And then you have a difference between S and R. proline here. And if we optimize this, we can get higher E, of course. So it's a kinetic resolution. We've also established the formation of these oxidinones by NMR. So here's the protected glyceraldehyde that we react with proline. So you can do it in situ, in solution, just mix proline with glyceraldehyde here. And then because there are diastereomers here between this chiral center and this one, so you can see the proton here and this proton that I showed here. And this is 2:1 sort of ratio between this material and this one. And this is the one from R. proline and this one S. proline. So we see that R. proline is reacting much faster with the S. one that proline is giving, the product proline gives. So we kept on going, and then we come into our manic reaction. Why don't we go back there? So we went back to this manic reaction, and here we saw a significant asymmetric amplification of this reaction. And in this case, we thought, okay, we do this. So we checked if this product can inhibit the reaction, and it does. because if you do this same experiment, you get 90% EE if you do the amine oxidation with racemic proline. But you can also have some parallel side reactions. You generate the dimer of this one as a side reaction, which also could contribute. But it's this kinetic resolution effect. And then I would hope that Gunther was here, because then the paper by Svetlana came, of course. Then she showed that this type of products, when it's acetone, here, this center is gone, can auto-catalyze this reaction. So we need to figure out maybe what's going on. Maybe it's something like that also. So I've written the table that we have there. This is in the paper. And this is what we did. Then we took this product, S3, put it in the reaction, and the yield that you see here is after subtracting the amount of that we put in on this catalyst. And we let it react for 5 days and hope that this will be improved, like autocatalytic. But we didn't get no significant yields here. Increase only 4. Okay, that's something. But if you compare the EE for the initial catalyst, you have 0, 25, 52. You see that it goes down. So we have a depletion instead. So the curve is like negative. But it's hard to prove it is autocatalytic. You know this is in equilibrium, so something is happening. And the spontaneous thing, I don't know if my student is too scared to write anything else than 0, because we measured this on 5 up to 5, so we have 0 again, So if this stays for 5 days in these conditions, it's still racemic, it's nothing. It didn't go to R or S. Or maybe he didn't want to write 1 here. So we have 0. And so we did this also for other reactions, for example, we changed the bulk, and you also have this effect. It's positive effect. Okay. Then we changed to our ethyl group. And you see you have a completely different shape when the ethyl group is present. It's like an S shape. And these are all homogeneous systems. So what is really going on? So we also did this experiment. So you take S-proline and you want to catalyze this reaction, and then you just add this aldehyde achiral as a pre-mix additive. So you mix them for maybe 40 minutes or 20 minutes. And then you divide the EE of the proline and you check what the EE is of this product. And then you can see here. So the top one is propionaldehyde, as you can see here. And the bottom one is isovaleraldehyde. And that one has a negative effect. Here, you look at when we had 99, it never goes up. So we did this experiment 6 times, it doesn't go up. So what could happen here? There are 2 things. This will have a huge effect here to go up here. But I think our product that we buy from Sigma is more than 99% E. But when we throw it into reaction, it could racemize a little bit. So it never reaches, maybe it's 99 at that point or something. So we are always sticking at this point. We never reach, we never went up. Even used it to pure proline. So maybe the product is a bit, we try to measure the EE, but we get like 99 again. So it must be very sensitive from here to come up there. So this is the explanation of why is it different shapes on these curves. Yeah, because it's diastereomers, of course. So here is the product, beta-hydroxyketone. So in the propionaldehyde, you have a methyl group here. But when you use, for example, isovaleraldehyde, you will have isopropyl group here. It's much more bulky, these 2 groups. And what we think then is, or we start to investigate, is that there will be a rate difference, of course, like in the first case. But when the rate difference is lower, it's not so big between these 2, then the effect becomes negative. Or if it will be intermediate, you have the S shape. But if it's much bigger, like in the propionaldehyde case, you have the positive amplification. So it's based on diastereoselective interactions between these. Okay, now we'll go to another important molecule, which is the ketones, the dihydroxyacetone. We originally tried to do these aldol reactions in water for synthetic reasons, because you can do sugars, of course, keto sugars. And as the same case as with the glycoldehyde, we got the sugars, but it's very poor EE of the reaction. You see here, is less than 10%, it's not asymmetric, but it could be diester selected sometimes. So we protect these ones according to Elnish, the first aldol here, and then you can see you can get a lot of high enough selectivity, and then it becomes synthetically useful. And you can also do the manic reaction again with that. But the important thing was here is that you can see that water can accelerate this reaction of the cyclic ketone dramatically. Because if you don't have water, this will take 5 days maybe, this reaction. And then we went back to another thing, because we wanted to make the full paper of that protected ketone. So we tried to use other amino acids for the full paper, of course, but we had a small amount of water. And then everything, all amino acids can catalyze these reactions, and a lot of them can catalyze it with high enough selectivity. So it was shown that you can use the whole spectrum of amino acids, and at certain conditions they can be efficient and they can give high enough selectivity. Now it was time for in the field to start to use primary amino acids as well, not only proline derivatives. And here's some transformations that you can do other carbon-carbon bond forming reactions with high enough selectivity using either primary amino acids or making them more acidic, like tetrazole derivatives. And you can also do Viking reactions with high enough selectivity and diester selectivity. So we looked at the transition state for this, and we compared the proline reaction, and also once again, it's one proline molecule, and in this case it's also one molecule in the transition state. And we have there with cyclohexanone the calculation according the aldol with the benzaldehyde, and that what gives the high enough selectivity is once again is the dihedral angle between the enamine, the chiral enamine here, and the distance between the oxygen and alkoxide formation here. You see this is different, for example, from this attack or from completely C facial attack, for example. So we could explain the stereoselectivity, origins of stereoselectivity in this reaction. And also one more thing that we saw is that for primary amino acids you get high enough selectivity when you have bulky ketones or cyclic ketones. But in proline you get high enough selectivity when you have linear ketones. And the reason is that obviously this rotates a lot. But in proline you have in the molecule you have the rigidity. So in this one uses the cyclohexanone to get the rigidity in the transition state. So at that time we also investigated nonlinear effects, also, of course, to try to establish. And then we saw also some S shapes, but it's linear. When you do it, we do always use catalytic amount, 10% or 30. But because we use a lot of different amino acids, they don't solubilize the same way as proline, of course, and don't behave. And then, that's when we started this research and came into this, we got in trouble. Because we went and we published these results with the serine, because this has a huge amplification. And this has been excellently, I won't clear it now, by Donald Blackmon, how this is why we get this. And that's because, as you know, it's the equilibrium between the racemate and the amino acid in solution which creates this. So you have much higher EE of the solution. And at this low catalyst loadings that we had, you can see it with serine, but not so much with others. And actually, 3 papers appear. My field is pretty competitive. So this one was first submitted by Hayashi in Agnievante in 2004. Actually, it came out in 2006. And he also showed the proline, how the crystal and it looks. And then you have the Blackmon paper, which explains the whole theory. And then Breslov also published a PNAS paper with this concept. But this is different from the papers, different from the theory I showed you with the aldehydes, because that's homogeneous and kinetic, and this is thermodynamic control. And that's important because all the ketone reactions are linear, if not these effects occurs. Okay. So next step, of course, we have done the primary amino acids, and what do we think next step? Of course, peptides, combinatorial chemistry, and we can do a lot of different views, and we can expand this concept. So the next step was to do small peptides, for example, D and 3 peptides, and just check them. So, and they work. And then we need to wet the solvent, and they're much more efficient than the amino acids. And you see here, you can get high selectivity and high DR for this reaction. And that means, like the next step, you can do, there's a lot of catalysts you can use. And there's natural peptides that we use. And one thing we started to notice is that peptides, they can work in water. They're much better than amino acids. You show you have 4 E's in amino acid, like 10% in water. But with the peptide, you can maintain the E. And you see here, there's some different conditions here. We did it phosphate buffer, and you get 83. Not so good here, but the E is high, I would say. And here is acetate buffer. The efficiency dropped because of the pH, I mean. And then you have still high E. And we also added some cyclodextrin, try to get a Breslov type hydrophobic interaction. But we got still high E, but didn't increase that much. And we have added SDS here because that will solubilize the substrate, because the ones we used in this case was not so soluble. But if you use the glycoaldehydes, you see, you can get excellent selectivity, or use dihydroxyacetone, you can get also high selectivity. And that's very important, of course, because you go from single amino acid, you have 10% E, you go to one dipeptide, you're up here already. It's like an enzyme, so you have this is the precursor for some DNA. So you start to get close, and you also get the D sugar. Here you start with S amino peptide, or you get D amino acid. They're directly related. So we calculated on the reaction with benzalide, as I did before, I showed you a couple of slides ago. And you see here that in this case, you have one additional hydrogen bond from the peptide backbone here. So this additional hydrogen bond makes a perfect lock here. So if you have made this reaction in water or aqueous media, it doesn't have so big effect. It doesn't distort the transition state by hydrogen bonding. So you can keep this pretty steady transition state. You get high enough selectivity. Okay, so I'll show you this slide because of course we do linear effect to see that. But this is unpublished result. So I want to see that maybe you guys can answer because you heard the crystal graphic guys. I just don't stay out this video. Here is with the alanine, you see it looks like this. And here it is eclectic and then it goes up. But for the dialanine, the same stereochemistry, you see you have completely a negative shape. So they have they can change dramatically the behavior of the amino acids, as you know. So it's very interesting. So you don't know what's going to happen. You can have depletion, you can go up, go down. And also want to show that the peptides can also catalyze Michael and other carbon-carbon bond forming reactions. And once again, it makes a very stable transition state. So let's go into the mechanism here. It's a bit complicated, but it's very important. I drew it because you see here we have the peptide starting peptide, and it's the same catalytic cycle as I showed you before. Post the medium ion here first, then you make the enamine, and then a stereoselective aldol reaction, get the medium ion again, hydrolysis, and you get the product. But it can also form this with, as I showed before, with the aldehyde, react with aldehyde, make this inhibitor hydrocyclic compound, or with the product to form this, or the donor. So there's a lot of things going on. And why is this important? Because this is going on every day in her body. But we don't want it. It's a very classical reaction, the Maillard reaction. If you eat the apple here, it's going to become brown. It's the proteins reacting with the sugars. But it's also what's going on in our cells. So if you have this, for example, dipeptide, it's very well known, this reaction. You form this iminium intermediate, again, as I showed you in the catalytic cycle. But this would be the product, actually, from the catalytic cycle. So if you generate it with low selectivity. So then, it will form this enamine on this side or this side, depends on what you have on this side. It's dihydroxyacetone, it will be on this side. And then it enolizes the optimization here. And you get the ketone, and you see the product is locked here, no? it's not reversible after this step, really. It could go back, but it's very slow. So it's slow. And what happens with these things? Yeah, it's well known in our body that it can create a lot of damage actually if you get these things. You can have further organization and the reactions I showed you, manic reactions, going on. You can have retroaldol, you also know, from this compound. You can have decompositions to get aromatic compounds. In all these things, it's known in medicine that it can create diabetes, for example, Alzheimer's, it can take part in, and also anything aging. So what is the final result? Death. So cell death. So this process, if it took, it's intrinsic that an amine or an amino acid or dipeptide will react in our body, and it with a carbon group. So this is going on because it could. It is like logic. It will react. But our enzyme is very efficient. That's where we live. So I wanted to finish with this slide. Because we all discuss origins of life and chirality. But actually, these ancient processes, the carbon-carbon forming in reactions and many, they all link also into the death. Because how the cell dies, we get age, we get older. So also in this lies the origin of death, you can say. They are linked. And here's my summary. But amino acid catalysis may hold the clues for the origins of molecularity. Amino acid catalysis is important for the origin of life, and amino acid catalytic carbon compounds can contribute to diseases, ultimate cell death. And this is not in this talk, but it's also useful for industrial applications. And I want to thank my group in the works with art here. And this is my present group here. And Isse did a lot of work, so his name is Abraham. And this is Pavel, did a lot of peptide work. And Jan, a lot of asymmetric catalysis, for example, oxygenation. Guling, a lot of heterocycle chemistry. And then we have Carl, the new guy, he's working on actually process development of cellulose, organic catalytic cellulose stations. And this is some form members that I'm very grateful for. And Peter and Fami here, they did the DFT calculations that I've shown you. And Professor Jonas Aprenis' collaboration with the peptide work. So, thank you very much.
Thank you very much for your talk, the time too. And I'm sure there will be any question. We start one. You need most of the time a free function in your system. When you go to the Easter.
Oh, it can do the reaction, but it's much similar, and the EE drops. So, but if you add an external acid, it could work. So, Yamamoto has shown.
Okay. Yes.
I must say that coming from the solid state chemistry, and when I look on Breshkov's experiment of the phenylalanine crystallization, Donna Blackman about that, what was the uniqueness of that? Because the formation of a pecticum, we know that for many, many years in the probable purification of materials. So what was the uniqueness of these two experiments?
I think what they will do is that to show how it's applied, what your knowledge is applicable to catalysis, because you see it in the reaction, but usually nobody does it.
I understand the point is that you've proven that this molecule, the enantiomeric proline, is a catalyst.
Yeah.
Or phenylalanine is a catalyst.
Yeah.
So the question is that if you crystallize non-racemic mixture and then you form a racemic compound, which is a stable product, I think this is known for centuries. So the question is, what was the uniqueness that was the noise behind it? I never understood that.
Oh, it was because it was a way to explain the non-linear effects we see in our reactions. That's why, and that will be one of the ways you could show that. If it's heterogeneous, but I agree with you. I think, but it's because it's linked to catalysis, I would say. But yours also.
No, the effect, I think the effect was known. I think the question is.
Yeah, sure.
Only could explain to me that this and problem with the organic chemistry, as I included. And they perform the reaction, and they look to nothing, only the initial product and the final product. And there is some precipitated there. It is ultimately problem. And there are hundreds of papers with this effect, with precipitate. And perhaps is the first one that look at the characteristic system, but the whole question is that with a little more get weather. It would look better with a little more, but this you must understand the synthetic organic chemistry mentality to understand the impact of the paper.
Yeah, but even if
in other cases, not to be explained. But the design.
If you take a Blackmon experiment, then I can understand. But when I read the Dressel experiment, where they took vanilla aluminum and you crystallized, let's say, I remember that 90%, and you got precipitation of the Rashamat and the 3% of the enantiomer in excess.
Yes, well, this is a practical experiment to demonstrate that for organic chemists there must be paid attention.
Thank you.
Yes.
Can I make a comment? I think Armando last September in Mexico City, and I asked how do you prepare the, let's say, air chlorine with 10% EE? He told me that you mix the solution, water solution, and I said that it's okay. May I just?
Oh, sure.
Example, let's say chlorine, chlorine with let's say 10% EE, 10% EE. One is one may prepare pure chlorine, pure chlorine, 55, and D chlorine, 45. The powder of this. The other one may be yellow chlorine, let's say 90, and yellow chlorine, 10 molar percent. This means so 45 to 45. Then this also is another way is to prepare air chlorine with 10% to examine the non-linear effect. One may prepare that by mixing enantio pure air chlorine 55 molar and 45. This means 55 minus 45 10. And other people prepare by mixing the DL chlorine 90. This means 45 to 45 and put enantio pure air chlorine is total 55 to 45. So the enantio should be. But there are experts, of course, they have also applied the expert in the organic crystal. So they are not the same.
No, sure.
They are not the same. So I wonder. In fact, Professor Hayashi is our colleague in the same building, and I asked him, so how do you prepare? So he prepared the sample by mixing these enantio pure L and B. So I told him, you need enantio pure chlorine to make the chlorine with low EE. So that's not important for prebiotic chemistry because you need chlorine. But the X-ray crystallography is apparently different from this. And also the reaction, of course, the chlorine is not soluble, is not very soluble in organic solvent. DMS and also the DMS, so it's not very soluble. It's not very soluble. And also Hayashi and discovered that in chloroform, when he tried to dissolve L-chlorine with 10% in chloroform, the EE of the solution is very high. high. But the important thing is not all of the substance is soluble. Only very small amount of the substance is soluble. That is
The question is if you're forming clusters of some kind.
No.
So it's really different, it's disconnected. In the moral form, we form a solvent. The black one showed that.
in some cases, but
diagram.
the solubility of the some of the parts they become soluble with some
Yes, but
solubility.
you get the eutectic composition at that point. This is quite well known. For the company which you collaborate with, they always check if your catalyst is a conglomerate or a semi-compound. And when you're lucky, it's a racemic compound. Because then you get with the eutectic far to the side. Because then you get the eutectic composition, that's a high EE. But when you have a problem and it is a conglomerate, you will get the conglomerate composition in the solution, which is 0% EE. And then you get this linear effect.
I want to say something in this comment because it's not so easy actually. Okay, usually, as I said, we dissolve it in water and you concentrate again. I don't know how I actually did something with this. But one thing is that if you, as you said, exactly, if you take pure product into chloroform and the demethyl is because that this chlorine is negative. But then you take an aldehyde, it becomes homogeneous because the first thing happens with chlorine. It forms aluminium as I remember from the mechanism. And then this one is equilibrium with the same. This changes. Okay, and this one goes directly into solution because then it makes chlorine soluble. So that's why usually you have a pre-equilibrium, and then your reaction is completely homogeneous because all these intermediates I show you, they start to act. So actually, only in the ketone case, you have this one. They won't form this one as easy, but it's very difficult. So in that case, you can see these the effects of the solid material much different from the aldehydes. Because they don't form these that are all soluble, these organic intermediates. And that's why we do low catalyst loading, because in the other ones they're like 4,000 mole percent actually. Black one equals 4,000 mole percent. So that's much more than your substrates are, and it's only the solids that is.
Everything starts from homogeneous condition, mixing of solution, then there should be no problem. And very often the people don't realize that they start.
But what I wanted to say is that both the ones I explored first part of the nonlinear effect and the second one, they always there actually nothing is only going on, and in the second, of course, both are actually going to happen in the system. Can happen. It's just how you look at it. But both effects.
One more. You started off by saying that the pharmaceuticals are in one or the other forms, but in the connection with thalidomide, it said that there is actually racemization going on in the body, so that actually the other form. I mean, it doesn't really matter whether it's pure or not. Is that correct? Because of racemization.
For the thalidomide case. I mean, then you get the other enantiomer, but I don't remember the exact mechanism in the bodies. I can very sure of you what it is. Maybe.
One is dangerous and the other not, but in the blood, there is racemization in the blood one. Then in
so is that therefore significant that actually, it's still significant that for some...
There's a lot of reasons. For example, patent as well. Because you want to patent your molecule 10 years more, you make it asymmetric. It's like Astra tries now with omeprazole.
Yes.
Then another reason, of course, is like in this case, one is active, one is inactive. But in your case, you have a resin. It's not with all drugs, but they will resinize.
Yes. I
So,
see.
so that's right.
I think there were tests for the thalidomide when it is on the mice, on the skin. Then there is a clear differentiation between the two measurements. But when it is inside, then the rationalization makes both. Okay, I think we have to stop the discussion. Thank you.
Thank you.